Thanks for coming. I gather it was fairly hard work getting out of bed. Well, it's going to get harder as you get older, unless I can do something about that. The main thing I want to tell you today is that we have a really good chance of developing medical technology that can truly do what you just heard, that can actually keep people in a state, both mentally and physically, that is typical of young adults, however long they live. And furthermore, that we have a good chance of developing that technology in time for most people in this room. Of course, because this is still at an early stage, I can't tell you for certain that this technology is going to arrive by a particular date. You know, any technology, the time frame is always very speculative. But I think that we have at least a 50-50 chance of developing that technology within the next 20 years or so. And of course, this technology will be able to be applied to people who are already older by that time. Now, the second thing I'm going to be telling you is that this will be rejuvenation technology. That means it will not simply keep you at the biological age that you are when you first get access to these new therapies. It will actually turn back the clock. So even if you're already 60 or 70 at that time, it will make you biologically 20 or 30 again. That's the kind of technology that I'm going to be talking about. So now that I've got your attention, let me tell you the real stuff. So I'm going to start by telling you what aging is. Now, this is a really weird thing that I would have to actually do this. But if you think about it, you know, we've known about aging since the dawn of civilization, and we've been pretty unhappy about it since the dawn of civilization. We've been trying to do things about it. So it's weird that if you take 10 people and you ask them what aging is, you will get 10 different answers. Even if you take 10 biologists and you ask them that question, you will get 10 different answers. That's not good. So I'm sure you all understand, as technical people, that the only real way to have a productive conversation about a technical matter is to start by understanding each other's language, by having a shared understanding of the definitions of terms. So that's why I'm starting by giving you my definition of aging. And this definition is useful in two different ways. First of all, it's a mechanistic definition. It says a bit about how aging happens, not really just about what it is. And the second thing, the big thing about this definition, is it helps to demystify aging. I want to emphasize here that aging is not a mystery. It's not an enigma. Aging is something that we understand pretty well already. And that's a very good first step in understanding and figuring out how to do something about aging. So, what is aging? Well, look at the middle of this slide, the second sentence. Aging is the lifelong accumulation of damage in the body, damage that the body inflicts upon itself. In other words, side effects of the processes that keep us alive from one day to the next. And that is exactly the same as it would be if I were defining the aging of a car or an airplane or any other simple man-made machine. It's not a fact of biology that aging happens, it's a fact of physics. Aging happens in any machine that has moving parts, whether or not that machine is alive. Once you understand that, it's pretty easy to understand a lot of other things about aging. Let me start with the sentence at the bottom of this slide. Aging doesn't matter at first. It only matters after the damage that happens throughout life, throughout the normal operation of the machine, has accumulated to a certain amount. And that's because all machines are set up to tolerate a certain amount of damage without any real decline in performance. All right, so that's my definition of aging. Now, I'm not going to move on to actual biological terminology, and I'm going to use other words. But you will see that what I'm saying, again, does not deviate from the definition I just gave you. Aging can be described in living organisms in just 3 words: metabolism, causing damage, causing pathology. Metabolism is the word that biologists like to use to denote the entire collection, the entire network of processes that the body performs in order to keep us alive. And as I said, throughout life, lifelong, even starting before we were born, metabolism creates damage. And damage eventually gets to a level of abundance that the body is not set up to tolerate, and that's when we get the pathologies of old age, the ill health, both mental and physical, of old age. So, of course, the goal is this. The goal, as you can see, I've changed the shape of the arrows a little bit. The goal is to weaken the link between metabolism and pathology, the link between being alive and being dead. So the question is, what's gone wrong? Why have we made so little progress in that endeavor so far? Well, I'm going to ask that question in a slightly different way, first of all. I'm going to say, why have we made so little progress against aging in spite of the fact that we've made so much progress against the problems of health that we used to have early in life? 200 years ago, even in the wealthiest countries like Germany, more than 1/3 of babies would die before the age of 1. And of course, there was plenty of death later in life, but not particularly late, like, for example, in childbirth. And now, we've got almost no death in the industrialized world at that kind of age. What's happened? How did we do that? Well, of course, you know how we did it. We did it by really simple ideas. Just figuring out that hygiene was a good idea saved a massive number of lives. And, mosquito nets and, really simple medicines like vaccines. And it's not worked against aging. So we must ask ourselves, why not? And most people would say it's this kind of thing. It's just the fact that aging is so complicated. Don't worry, you're not supposed to be able to read this slide. The point is that so many things go wrong when we get older, and they go wrong at more or less the same time. So they interact, they exacerbate each other. And it's all like, most people would say, well, this is why. The sheer complexity of aging has overwhelmed the ability of medical researchers to get to grips with it. And of course, the same is true if we look at the other end of the process, the beginning, metabolism. What I'm showing you here is a biochemical chart. This is a simplified diagram, all right, of a small subset of what we know about how the body works. So I'm guessing there's plenty of people here in the audience who write software. Hands up anyone who writes software. All right, so you all can see immediately that this is the ultimate catastrophe of uncommented spaghetti code, right? There is no way in the world that we would be able to tweak this network in such a way as to stop it from doing the thing that we don't want it to do, which is the creation of damage, without at the same time having unintended consequences that will stop it from doing things we need it to do to keep us alive. It's just not going to happen, right? Most people would say that's the main reason why we've made so little progress. And that complexity of metabolism and also the complexity of the pathologies of old age, those two things are certainly really important. But the real reason why we've made so little progress is because we've been stupid. As far as I'm concerned, it's complete common sense that there's a way to sidestep all of that complexity. So if you are trying to attack the pathologies of old age directly, that's what I'm calling the geriatrics approach here, then what that means is you are effectively hoping for the best that you can overcome the complexity of pathologies, that huge list of problems that I put up 2 slides ago. And it's not worked, right? It's just too complicated. Plus also, fairly obviously, it's just intervening too late in the chain of events. If you try to attack the pathologies, then your therapy is going to get progressively less effective as the person gets older, because the damage is still accumulating, and the damage is causing the pathologies. Similarly, if you try to adopt an approach of effectively cleaning up metabolism, which is what I said earlier, tweaking the network that I showed you on the previous slide, again, you're just not going to get anywhere because it's just too complicated. That's what I'm calling the biogerontology approach. It's what people who call themselves gerontologists tend to look at. But there is this perfectly obvious third approach, which I'm calling the maintenance approach. The maintenance approach says, let's go in and periodically repair damage. Okay? Now look at the diagram and see what that means. What it means is that we don't need to try to clean up metabolism. We can let metabolism create damage at the natural rate, at the normal rate. Furthermore, we don't have to clean up pathologies because we're not going to let the damage accumulate to a sufficient level to cause the pathologies in the first place. And by doing both of those things, we are sidestepping all of our ignorance, all of that complexity. We don't need to understand metabolism because we're not going to mess with it. We don't need to understand the pathologies and how they interact and so on because we're not going to let them happen in the first place. The only thing we need to understand is the damage itself. Not how it's created, not how it causes problems, just what it is. Now, we already know that this works. Remember my definition of aging. I was telling you that aging is a phenomenon of physics, not a phenomenon of biology. Aging is just the same phenomenon in a living organism or in a car. So here's this car. It's more than 100 years old. How did it get that way? It did not get that way by being designed to last 100 years. This car was probably designed to last 10 years, 15 years at the outside. And yet here it is. How come? Simply because its owners, the people in the car, and the people before that, and the people before that, they decided to look after the car unusually well. Most of us, we don't look after our cars any better than what the law requires. And sure enough, the car falls apart pretty much at the age that the manufacturer expected it to, and we go and buy a new one. There are only a few people who are crazy enough to do this very comprehensive amount of preventative maintenance to their cars that will allow them to live a lot longer than they were designed to live. And that's what's happened here. So we know that it works. And the only reason why we can't already do this to the human body is because the human body is substantially more complicated than a car, and therefore the damage repair processes that we need will be substantially more complicated, and we haven't developed them yet. But the fundamental reason we haven't developed them yet is because it has taken so long for anybody to notice that actually aging is a phenomenon of physics, and all we need to do is preventative maintenance. So now, is this really promising? Well, I've told you what aging is, and I've shown you that comprehensive preventative maintenance is the obvious way to go. But we are still left with the question that I'm showing you at the bottom of this slide. Yes, preventative maintenance is the common sense approach. But the body is more complicated than a car. In fact, the body is more complicated than any man-made machine. And even though we are sidestepping all of our ignorance of metabolism and pathology, we still have to worry about damage itself. How complicated is the damage? If it's really, really, really complicated, then we haven't really achieved anything by this idea. We still don't know what to do. Luckily, it isn't all that complicated. It's more complicated than the damage in a car, for sure, but it's nothing like so complicated as metabolism or pathology. And the way I'm going to explain that to you is by classifying it. What we have here is, you can think of it as a taxonomy of damage. Look at the left-hand side of this table first. The left-hand side is a list of types of damage, categories of damage. There are many. What's going on there? Fuck off. What's going on there? Give me my. I've got to talk about that table. I can't really go on unless we have that table back. Oh, all right. Thank you, whoever said that. All right. So, yeah, there's 7 different categories of damage. Now, look what these categories are here. These are really, well-defined, concrete biological phenomena. Cell loss, what is that? It's simply cells dying and not being naturally replaced automatically by the division of other cells. So, of course, if that's happening, then the number of cells is going to go down. Eventually, in whatever organ that's happening in, there won't be enough cells to do the job. So we'll get some pathology. If you want to ask, is there some aspect of aging? Yeah, I'll come to that. Some aspect of aging in which cell loss is the driver. Well, let's take Parkinson's disease. Parkinson's disease is something that's caused by the death of cells in a particular part of the brain called the substantia nigra. And those cells are responsible for making an important chemical called dopamine. Eventually, we don't have enough of those cells. All of us lose a lot of those cells during life. Some of us lose those cells a bit more rapidly than other people, and those are the people who get Parkinson's disease. So that's an example of an aspect of aging caused by cell loss. If you go down the list, you can see other things that you'll recognize. Division-obsessed cells, what are they? Simply cells dividing when they're not supposed to. And you can immediately see that that's pretty much the definition of cancer. If we look at intracellular junk, what's that? Molecular waste products that accumulate inside cells. Turns out that that's why we get atherosclerosis, which is the #1 killer in the Western world. The accumulation of fatty deposits in our major arteries gives rise to heart attacks and strokes, so it's the #1 killer. I could go and talk about more of this list, but I won't do that right now. The point is, there's only 7 categories. And the really good news, of course, is the right-hand side of this table. The fact that for each of these categories, we can describe a generic approach, an approach that works for every example of damage within the category. So there are many different organs where we have cell loss, but for all of them, we should be able to reverse that cell loss to put new cells back just by using one or another type of stem cell therapy. If you think that's exactly what stem cell therapy is, right? We put cells into the body that have been pre-programmed in the laboratory into a state where they will divide and differentiate, transform themselves into replacements for the cells that the body is not replacing on its own. That's all that stem cell therapy is. And sure enough, stem cell therapies for Parkinson's disease are looking very promising right now. This is the kind of thing that needs to be done. Now, I'm the Chief Science Officer of a foundation, a charity based in California, that does biomedical research. You might ask, why do we exist? We exist because a lot of the work that I'm describing here on this table, on the right-hand side, is not being done. We hardly do any stem cell research, even though it's very much an important part of this list. The reason we don't is because all of the really important stem cell research that needs to be done to actually address all of the various types of cell loss that occur during aging, all of it's already being done by other people, because stem cell therapy is understood. The research community and the world in general understands that stem cell therapy is a very established, very legitimate, very promising approach to treating a lot of different diseases, including a lot of aspects of aging. But there are many aspects of aging for which that's not the case, for which there are ideas for developing the maintenance approach, for repairing the damage, but those ideas have not really got traction within the medical profession or the medical research community. That's why we exist. And we work on all of the other things that you can see on the right-hand side of that table. Here's just a list of a few of the papers that we've had out over the past few years. We publish in the academic literature just like anybody else, and this is one of the ways in which we validate the importance of our work. And I'm very proud to say that we've been able to unblock a lot of very strong log jams in research. We've been able to get things moving that have been stuck and not moving for more than 10 or 15 years in various of these areas. I'm just going to spend a couple of minutes talking about one of our projects so that you appreciate that I'm not just bullshitting you. This is a project that we have worked on atherosclerosis. So I mentioned atherosclerosis is the #1 killer in the Western world. This here is how it begins. Atherosclerosis begins when white blood cells infiltrate the walls of our major arteries for the purpose of cleaning up garbage, detritus that is stuck in the artery walls. And those white blood cells are very good at doing that, and they can normally do it very well, but there are some contaminants in that detritus that they are processing, contaminants that they do not know how to process. And those contaminants build up, and they eventually poison the white blood cells, and the white blood cell turns into this thing called a foam cell. You can see this thing called a lysosome in the middle of the picture, which is part of the cell that is inactivated. And after that happens, the cell fills up with globules of fat, as you can see. Horrible thing. Now, this would not happen if the white blood cell had machinery that could simply destroy the contaminants. And luckily, we know the chemical nature of those contaminants. We know that these are certain oxidized cholesterol derivatives. Normal cholesterol, no problem. But oxidized cholesterol, big problem. So what we did was we found bacteria in the environment that had enzymes that were able to break down oxidized cholesterol. And after a lot of fiddling, we were able to modify those enzymes so that they work in a human cell. And we put them into human cells, and sure enough, the cells are protected. This is a graph from a paper we published a few years ago showing our effects. Essentially, the height of each of those bars denotes how healthy the cells are, how happy the cells are. So a short bar means the cell is very sick, a tall bar means it's very healthy. And the groups of bars denote different concentrations of this toxic contaminant that I was talking about. It's called 7-ketocholesterol. So you can see that in each group, the right-handmost bar is the tallest. And that says that the cells are healthiest. The other bars in each group are what are called negative controls. So they are cells which do not have this extra advantage, cells that don't have our magic enzyme, or they've got a different enzyme, or they've got the right enzyme, but it's not been modified in the correct way. So you can see we're pretty happy about that. And it's getting traction now. We've got a lot of community support. This is our research advisory board, a bunch of extremely world-leading scientists who endorse this approach very strongly. What's even better is, these days, people are reinventing this maintenance idea and pretending it's original. This paper came out 4 years ago, and everybody is referencing it. Everybody is citing it. So, and it's identically the same idea. This group of scientists chose to divide aging into 9 categories rather than 7, and here are their corresponding interventions. Their graphics were a bit better than mine, so maybe that's why they got more traction. But the main thing is, it's now a very mainstream, very established idea. So you don't have to be thinking, well, you know, this strange guy with a long beard is standing here talking this stuff, but it's obviously some kind of eccentric idea that's not really true. That's not the case anymore. This is genuinely an accepted paradigm now. It's coming. Now, some of you may have heard that I think that people alive today have a good chance of living like 10 times longer than people live today. And that is true. But that's not what I want you to go away thinking about after this talk. The thing about our work is we don't work on longevity. I think it would be great if people could live longer in a totally youthful state, both mentally and physically. Because let's face it, people who are healthy tend to want to carry on enjoying their lives. It doesn't matter how long ago they were born. And of course, nobody wants to get sick either. Longevity is a side effect of not getting sick. I mean, think about it. People tend to die from being sick, right? So if we stop you from ever getting sick, then we're going to, on average, have you live longer. But that's not what we work on. And the reason I need to emphasize that so much is because it's incredibly easy to think, oh dear, if we extend life, we're going to extend the nasty part of life near the end, where nothing really works very well anymore. That's not what this is about. We're all about keeping people youthful, and any longevity benefits are just a side effect. So whenever you see me in the media being described as some kind of prophet of immortality or anything like that, just don't pay attention. That's just sensationalism. If you want to know more about the biology here in less than the 2 seconds I have left, then please get this book. I published it several years ago, and it covers all of the biology of aging in great detail and how this is all going to work. It was also quite recently translated into German. The German version of it is called Niemals Alt. I don't have a slide showing you a picture of the front cover, but you can certainly buy it in all the usual online places. I encourage you to do that. And I also encourage you to send us, to have a look at our website, and you're perfectly free to email me at any time. I think I've run out of time, so I won't be able to answer any questions now, but thank you for your attention.
Aubrey, thank you so much. You can stick around.
Okay,
thank you.
Yeah, I will.
You can stick around for just 1 or 2 questions.
Okay.
We decided, so many people got excited, and thank you for upvoting the questions. I'm just going to do 2 questions so we can cover these. The first one is, could solving this problem too soon be possibly catastrophic for humanity?
Mm-hmm. Yeah, it's a great question. So if we really solve it too soon, as in tomorrow, then it would be messy. There would be a lot of problems to solve very quickly. But the good news is we're not going to solve it tomorrow. I mean, it's bad news in that lots of people are going to die before we do solve it. That's bad, right? But the thing is that we've got time to work out how to make the transition into a post-aging world a smooth transition. So, for example, people terribly worry about, here's the question, right, overpopulation, shortage of natural resources. The thing is, other technologies are already coming along that are solving that problem. We've already got that problem with climate change and so on, right? But that's what we're going to solve with cheap solar energy and, desalination technology and artificial meat and so on. We are going to be increasing the carrying capacity of the planet far faster than we will ever have any increase in the population of the planet. So I don't believe that that's ever going to be any kind of problem. There are plenty of other problems that people raise, how we pay the pensions. Well, hello, there won't be any fucking pensions because we're not going to have any jobs anymore because of robots, right? Same deal, right? So, and we can answer all of these questions. Some people say, won't it be boring? Well, my answer to that is, if I've got a choice between getting Alzheimer's at the age of 80 or being bored at the age of 150, I damn well know which one I'm going to choose. So, these are the kinds of answers. And you've got to actually think about these things before getting too worried about them. Go on.
All righty. I saw it's a tight one here, but I want to make it quick. So I hope you accept that I'm going to pick the quick one here. I am now 50. Will I make it?
Well, I'm 54, and I hope I'm going to make it. But as I said right at the beginning of the talk, I cannot guarantee. I do not know how long these things are going to take. I think there's a 50-50 chance that we will get these technologies in place within about 20 years, but I totally accept that there's at least a 10% chance that we won't get there for 100 years because we come across a whole bunch of new problems that we don't know about yet. However, I will say one thing. That 20-year estimate is from the assumption that we're not going to be held back by shortage of funding. And at the moment, we are being held back by shortage of funding. I believe that we need desperately to add a lot of money to the tiny amount that we currently have to move this forward. Our foundation only has $4 million per year. Just one extra digit on the end of that would probably speed up by a factor of 3 the rate at which we're getting this done. So that's huge. That could be like 500 million lives that we could save, just with another few tens of millions of dollars. So any billionaires in the audience, see me later. And also, I like to point out, the less wealthy, the poorer you are, the more people you know who are wealthier than you are. Think of that, right? Now that means, I say that, I'm not just joking there, because the point about this is advocacy is everything. I want to really thank the organizers of this meeting for bringing me here. I spend my life on the road giving talks like this, giving interviews and so on, and the reason I do it is because we absolutely need to raise the quality of understanding of this issue, the fact that this is not only a desirable thing, but a feasible thing, so that people actually get on and apply the resources to get it done as fast as possible.
Thank you so much for inspiring us. Thank you.